So, does anyone have any specific requests? Oh, I see. Okay, we could do that. Does anyone have any specific requests about some basic trig? Like, so I've got some math people in here. I've got some science people in here. Do you need some help with basic ways to remember some trig values? Yes? All right, let me start there. I'm going to start with some basic stuff. And then if you have questions, go ahead and throw them in the chat. Put like a Q in front of it so I can kind of keep up. So if you had anything you came to this workshop hoping to get, please put that in so that I can make sure to get there. Okay, so let me do this. I already see Phil. You're not here very secretly because they could all see you. Okay, I see. Okay. I should have put some vector worksheets up there too. Oh well. All right, so everybody can see my whiteboard? Yes. Now, I'm assuming we all know the real basics of trig. Is that an okay assumption to make? Can somebody tell me a very basic definition of sine just to kind of get us started? All right, I got you, Eric. We're going to start with some more basic stuff. Can somebody tell me anything about sine, some basic definition of sine? Anybody know anything about sine?
Sine is opposite over hypotenuse.
Okay, so we got, if we have a triangle with theta, so we got the opposite, the hypotenuse, and we got the adjacent. So it's opposite over hypotenuse. Now, to be really, okay, I really want to listen to you guys. Does anyone else also think of it that way?
Sine likes y.
Ooh, look at you. Of course, you're one of my students, so you know how I feel about the SOHCAHTOA stuff. Let me make some notes before somebody leaves. Yeah, I'm going to definitely talk about vector stuff. So you're saying subtracting two vectors. And sorry, this is just for me for later. Oh, yeah. Okay, so magnitude, direction, maybe even adding vectors and getting the resultant magnitude and direction, yes? I would think. I'm going to just do that. Okay. This is obviously just for me because it's especially poorly written. Okay. Now, let me do my little spiel. I do not want to take, you guys know SOHCAHTOA? You guys know SOHCAHTOA? Anybody not know SOHCAHTOA?
It sounds familiar, but I don't really remember what it was.
So look at the first three letters. So, sine, opposite, over hypotenuse, SOH.
Yeah, it's coming back now. Yeah, that makes sense.
Cosine would be adjacent over hypotenuse. Tangent would be opposite. Now, listen to me. This has such little usefulness. It makes students feel better because I think most students want something like this to make it like, oh, but all right, let me see if I can win anybody over. If I put a triangle like this with the angle and the base, sine is the y side over the hypotenuse. Sine, like somebody said earlier, sine likes y. Sine is related to the y piece. So if you think about vectors and you have to break something up into its components, right? It's so much easier to me to remember the sine gives me this piece. It likes the y and cosine likes x. Cosine theta would be x over hypotenuse. Now, has anybody ever heard that besides Zoe? Because she has me as a teacher, so of course she's heard that. Anybody else ever heard this idea that cosine likes x, sine likes y?
Not really, no.
No? Does it make any sense?
It does. I just haven't heard of it before.
All right, now let me make it make even better sense. Okay. So somebody, let me change colors here. Okay. So if I've got a nice unit circle, everybody pretend with me that that's a circle. Okay. At 0 degrees, what is sine? So here,
0.
0, because sine likes y. Sine is related to the y piece. How big is the y piece at 0 degrees versus, let's say, 90 degrees? You guys with me? No? So let's go to 30. Let's go to 30 degrees. If I am at 30 degrees, can you guys see the y piece? Isn't the y piece here? Stay with me now. Oh, Eric, go ahead. Sorry.
I was wondering, you keep repeating that sine likes y, but
Yes.
I think I may have missed like what that really means. Like, what do you mean by how does it like y?
I love it. When I say sine likes y, that is a remarkably anti-technical way to remember this, correct? It's not an official definition. It doesn't even really make sense. I understand. But it's a way to remember that sine is related to the y piece of a triangle. Sine is the ratio. If I put the angle in the base, sine is the ratio of the y piece to the hypotenuse. Why am I calling it the y piece? Because that's the y-axis here.
Okay.
And here's the x piece. Now stay with me. I really, really want you to understand how this helps you remember basic things. What's happening to the y piece as my angle gets bigger?
The y gets bigger?
Yes. So what is true about the y piece at the x-axis at 0 degrees? How big is the y piece at 0 degrees?
0.
Is everybody with that? Do you guys see that, everybody? At 0 degrees, there's no freaking y piece. It hasn't lifted off of that at all. So of course there's no y piece yet. It's like having a triangle just flattening it. So there's no y side. So that's why the sine of 0 is 0, because sine goes like the y piece. So when there is no y piece, sine is 0.
Okay.
So it's going to get slowly bigger, right? 60 degrees is going to be even bigger. And of course, it's going to get biggest at 90, correct? Now, watch this. Watch this. This is something I made up for myself. And let's see if you guys appreciate it. Does anyone remember what sine of 30 degrees is?
I think it's pi over 3.
1/2.
I think what you're doing, real quick, whoever said the pi over 3, you might be trying to make 30 degrees into radians, which is a whole other thing. 30 degrees would be pi over 6 radians. Right, so we'll talk about radians here in a minute.
Okay.
What did somebody else say? I'm sorry.
0.5. 0.5.
Okay, if you put it in the calculator, 0.5. So it's 1/2. So now watch this. Does anyone remember sine 45? And then I want to show you something kind of nifty. 45 is nice because it's where cosine and sine should be the same. The x piece and the y piece would be the same. What's sine of 45? Don't tell me the decimal. I don't care what your calculator says. What is sine of 45 degrees? Anybody? All right, let me tell you. Okay. Oh. Yes, all right, I like it. So there are proofs you can do for these values. I'm not going to focus on that today unless somebody wants to. But watch this, watch this. I love this, watch. Isn't the square root of 1 still 1? You guys with me? Isn't the square root of 1 still 1, yes? I'm just going to go, yes. What's the square root of 0? What's the square root of 0? 0. So look at this progression. Square root of 0 over 2, square root of 1 over 2, square root of 2 over 2. What would sine of 60 be if that keeps going? Square root of 0 over 2, square root of 1 over 2, square root of 2 over 2.
Square root of 3 over 2. 2.
Holy shit. Is it square root of 3 over 2? Do you guys remember? Does that sound familiar? Nobody remembers? Man, you're in the right place. Okay. Hopefully that's striking a bell. And keep going. Keep going. What would sine of 90 have to be then? Square root of 0, square root of 1, square root of 2, square root of 3 over 2, square root of
4?
4 over 2. What is the square root of 4?
2.
What's 2 divided by 2?
1.
1. Yes, doesn't that make sine of 90? Why is sine of 90 1? Because sine likes y. And at 90 degrees, what axis am I completely sitting on? Freaking y-axis, right? So sine's going to be the biggest it could be. Since it's in the unit circle, the biggest it could be is 1. All right, let me stop for a minute. Does anyone appreciate that amazing pattern that's just there for us? What is
The sine likes y concept kind of came full circle when you
Yes.
said that sine 90 equals 1.
It doesn't stop there. This is what kills me about this. And again, if you love SOHCAHTOA, I am not shitting on SOHCAHTOA. It's fine. It's just, it really is not smart for us to teach that, because sine being related to y is just as easy as teaching this, and it carries forever after that. Knowing that sine is related to the y piece of a triangle when the angle's in the base is huge. It carries through so much into vectors. So anyway, sorry. So I'm kind of over us teaching SOHCAHTOA, but again, if you like SOHCAHTOA, it's got its uses. I'm not trying to tell you it's bad for you or whatever. It's just would be better if we taught this from the beginning the same way. Anybody having any trouble with what we've done so far? You guys okay out there? All right. What does cosine do? Oh, got a chat. Hold on. You're good. Okay. I really want to make sure you guys get what you need out of this workshop. So I need you to stay on top of me if I'm not giving you what you wanted from this workshop. What does cosine do related to what sine has done here? What does cosine do? Does it have different values? Like, what's cosine of 0?
1.
Yes, because cosine likes x, it's going to start maximal. Yes? Does that make sense? And of course, it's going to march through this whole thing backwards. Okay. Because what's the most basic trig identity? How does sine and cosine relate to each other? What must they do? Does anyone know?
Inverse of each other?
Say again?
They're inverse of each other?
No, be careful. They're not inverses of each other. What about equals 1, Gani? What has to equal 1? What's wrong with this?
Would it be sine squared theta?
There it is. So sine squared plus cosine squared is 1.
Yeah.
And that's just because they're in a unit circle. In a unit circle, x squared plus y squared equals 1. That's the definition of a circle, right? So if you know sine is the y piece and cosine is the x piece, this identity makes so much more sense immediately. Okay, maybe. Okay. So that's some basic stuff. This is just at the level of remembering important values. What's up, Eric?
You said sine squared. I forgot what that symbol is called. Forgive me. But
Okay.
sine, is that you said theta?
Yeah, theta.
Okay. Sine squared theta plus cosine squared theta equals 1. So does that mean sine squared theta plus cosine squared theta is the whole circle?
No. So I could do a little, all right, real quick. Let me see if I can do this quickly. I'm going to take this stuff away over here.
Okay.
See if anybody starts yelling at me. I mean, I need a big eraser. I need like an Etch-a-Sketch eraser. All right, there we go. Get out. Let me redraw this poor little line I just lost. I always forget I can make a straight line. Okay, that's sort of straight. Okay. On a circle, the really cool thing about a circle is, real quick, a circle is the collection of all points that are the same distance from a point we call the center. So if the center is at 0, 0, oh boy, real quick. I don't know if you guys remember this. And let's just do this more directly. I was going to use the distance formula. Screw that. If this is X and this is Y, can't I use Pythagorean theorem right there? Every
I guess, yeah.
point on that circle creates its own little triangle, its own little right triangle in which this is true. This defines the set of points that live on that circle. Every point in that circle must work in this equation.
And by the circle, you mean everything in the triangle, or?
The interesting thing is every point on this circle would create its own triangle, which we could then have a Pythagorean theorem that, and every single one of them says the same thing. The X side squared plus the Y side squared has to equal the hypotenuse squared, which is 1, because we're assuming it's the unit circle, right?
Mhm.
Now I could go deeper into circle equations, but I don't really want to do that. So if you want more about circles, you can always ask me, I think, at the end.
Okay.
But that is key. That is a key thing to understand to build trig on, is the idea of the unit circle, any circle really, and then you can talk about radius 1 circles. Okay. All right, now, I think this is going to be weird for me because I got most of you don't need a lot of the math stuff, and I think just one of you needs the math stuff. So let me do this. Let me talk about vectors, because I think most of you need this kind of information. Did anybody else have anything basic that they wanted to ask about? Like, are you okay with tangent? And then what are the other? Let's do this real quick. I'm going to erase everything I've got up here. Are you ready? Well, except for this. Let me do this. I'm going to see if anybody starts to yell at me. I got a chat. Oh, shit. Yes, of course. I got you, Phil. Don't let me forget radians. In fact, let's talk about radians right now before I go any further. Because I did say I would. All right. What the hell are radians? What are they? Where did degrees come from? How many total degrees are there in a circle?
360.
Yeah, all the way around a circle is 360 degrees. Does anyone know where that came from? Did it have to be 360? Have you ever thought about that? I'm sorry, Eric, do you still have a question, or is that from earlier?
Oh no, I just forgot to lower my hand.
You're okay,
Sorry.
you're okay. Do you guys, this is really interesting. There is no reason that it had to be 360. 360 is kind of related to, 60 minutes, 60 seconds. 60 is such a beautiful number because it has so many factors. 360 degrees has so many ways to break it up. You guys understand what I mean? I could factor 360 in a multitude of different ways. It could have been 400 degrees. It does not matter. This number we picked was kind of arbitrary. Did anyone ever hear that or know that? Does what I'm saying make any sense to you? You've never heard it, but does it make, it is weird. Yes, please let your mind be blown a little bit. You really should know this. Did anyone ever think, why is it 360? Or did we just kind of go, of course it's 360. They said it's 360. There's no reason it could not have been 400 degrees or 80 degrees or a law of math. I love it. Okay, so you guys are all getting to a point where you should feel very comfortable investigating why the hell things are the way they are. This is one of the things. There's nothing special about 360 except, like I said, it could be broken up in a multitude of ways. So we like it because it could be broken up into little parts real easy. Let me see what I got here. Exactly, totally. Now stay with me. Radians kick so much ass because they are not made up. They are actual physical distance. They're not completely made up. 360 is completely made up. Right? Next time you're with a math teacher, say, hey, is 360 degrees kind of made up, and see what they say. Okay, so what the heck is a radian? A radian, if I take any circle, and again, every time I draw something and say it's a circle, we're just all going to pretend it's a circle, okay? If I take any circle, it's got a radius by definition, correct? Now here's what's really cool. Let me see if I could do this. If I take that radius, what color do I want to use? Let's go with, oh my gosh, let's go with dark red. So if I take this radius and I curve it and I place it down on the circle, I really want this to make sense. So I've taken this, I've taken that and I brought it over here. You with me? I took this and I brought it over here. Then I curved it and then I put it back on the circle. Yes? Can you guys see that? Can you guys envision what I've done? So you can imagine this is like iron. I took it out of there. I bent it exactly to be the same curvature as the circle, and then I put it back on. Yes? Okay, now, a radian is simply the distance that I would go if I traveled the distance of a radius along the circle. So this right here, this is 1 radian. Now listen, the beauty of this, the real beauty of this is twofold. One, it's not made up. It is based on actual physical measurements. So it's a natural thing about the circle itself to use to talk about where I am in terms of angular change. This is completely made up, right? Now, the second thing that's really cool about this, what if our circle gets larger? What happens to its radius now? If this circle kind of blows up to be this big, what's true about its radius? Is the radius the same for the blue circle now? Is the radius the same?
It gets bigger.
It gets bigger. It gets bigger proportionally to how big the circle got. So if I took this radius and I laid it down on this circle, it would go to the exact same place. All right, now this is really key. Does that make sense? If the circle gets bigger, the radius gets bigger so that when I curve it, it goes right on the circle, the same angle, the same angle. Let me stop for a minute. I really want you to understand this, because the more you understand what I'm doing right now, the more you really understand radians and why they are so preferred by math and science people. So it kicks ass. If I made the circle small, little tiny, look at that little tiny baby circle, and I took its little tiny baby radius and I curved it, it would go to the same angle. So 1 radian is the same measure no matter how big or small the circle is, which it has to be, right? They're supposed to only care about how wide this is, not how long it goes out, right? It's supposed to be the same angle measure no matter how long these go. Okay, I want you guys with me. Everybody sort of with me? I keep checking in with you guys. Now.
Yeah, it makes sense here.
I'm going to erase this red stuff. This is old stuff. I'm going to erase this red stuff. Here it goes. Go away, red stuff. Do not be too crazy with my erasing. Red stuff, go away. Leave me now. All right, this is going pretty well. I like it. It's better than trying to erase a whiteboard. Okay. Except I can't get high off of my markers. I could do that with a whiteboard. Now, what was I about to do? Let's see. I honestly forgot what I was about to do. Shoot. Oh, there we go. There we go. Okay, I got it. I got it. So let's make the connection. Okay, so let's make the connection between radians and degrees. Do you guys understand? Let me ask you, do you understand how it doesn't matter how big the circle is to talk about radians? Because as the circle gets bigger, the radius size gets bigger. So let's talk about a unit circle. Let's talk about a unit circle. So what is a radian in a unit circle? It'll be 1 radian, 1 radius is worth, right? So how many radians is this? So can somebody tell me what is the circumference of a circle, of course? You guys know. What's the formula for the circumference of a circle? I like it. 2 pi r. When I first looked at it, I'm like 2 per. I mean, no, I know what you mean. 2 pi r. I like it. So in this case, what is the circumference? What is the circumference of this circle? It's 2 pi because the radius is 1. Is that cool? Is that cool? Okay. What that means is how many radians, how many of these could I lay down to get all the way around the circle would be 2 pi of them. So a complete way around a circle in radians is 2 pi radians. But you can basically see from a formula, to be honest, and like I said, it doesn't matter if we're in a unit circle or what. Isn't r the length of a radius? So how many r's does it take to get around a circle? 2 pi of them, right? You guys with me? A radian really is just a radius curved and put on the circle. That's what a radian is. It's the amount of angle that I go through to match that right here, to match where the radius would end. That's how big a radian is, this much. And of course, how many degrees is it around there? It's freaking 360, Jeff. You asked us that earlier. Oh yeah, 360 degrees. So if 2 pi radians is 360 degrees, oh, let me see. All right, good question is here. The arc length for this, if I go through, you're getting a little bit ahead of us, but we can deal with this. Yeah, so for right now, I'll say this. It's focused, we call the angle here 1 radian, but I want you to realize it is, how do I say this? Do you see this little circle that I've kind of drawn part of right there? Do you guys see that? This is a very technical little point. And I'm kind of saying, here's where the angle is. Don't we normally do that for angles? Don't we put them like right there, right? If I'm up here, we put a little line, that's where the angle, we can put the angle next to that. Isn't this 1 radian for this circle? Isn't that 1 radian for that circle? If you understand that the answer to that is yes, then that means you understand everything I just said.
Yeah, technically it is, right?
Yeah, you could say technically, but it just is by definition. So when you say arc length versus angle, in terms of radians, they're the same. Now there's going to be some translation between them, considering how big the radius is. Okay, maybe. So that's 1 radian. So right now we're going to focus on it being an angle measurement, and then we can get a little bit into transformations, but I don't know if you're going to have to do a lot of that. For right now, let's finish this out. This is between radians and degrees. Has anyone ever seen this? If I divide both sides by 2, I know that pi radians is 180 degrees. Does that sound familiar to anybody?
Yes.
Not really, but it makes sense, yeah.
So what is pi over 6 radians? Isn't it just 30 degrees then? Does that sound familiar? Pi over 6 is 30 degrees. No?
Oh wait,
No.
why did you put the 6 there?
just as an example. I'm sorry, let me take it away. So let me leave this as just a fact. This is a fact. Halfway around a circle, didn't I go half of 2 pi? Didn't I go pi? But didn't I also go 180 degrees? Those are each of those is a way of describing this motion. So if I'm on a circle and I go this far, how many degrees did I go? How many degrees did I go right here? This is the
180.
180 degrees. Didn't I also go half of 2 pi?
Yeah.
Come 0. So this is also well, yeah, let's go ahead and do it. 2 pi divided by 2. This is pi radians. So pi radians is the same thing as 180 degrees. It is exactly like our made up freaky units based on the measurements of a king of England for foot and so forth, and how to convert between feet and meters. That's kind of like what this is. We have made up shit, degrees, which is useful. It's fine. It's fine. And then we have how to convert that to the thing that makes more sense, radians. It's pretty much exactly like feet to meters. Okay, let me stop for a minute. Okay, maybe. So somebody can, so looking at this, if pi radians is 180 degrees, then what's pi over 3 radians? If pi is 180 degrees, what's pi divided by 3?
60
degrees.
degrees.
All right. Does anyone who's ever memorized their trig, do you know that pi over 3 is 60?
That's from the unit circle, isn't it?
Yes, exactly. Of course. I love it. But now you can see, I mean, this is probably the way that your teacher told you, but it's been a while. So it's probably the same way your teacher explained it. Okay. Let me stop there. Any questions about radians versus degrees? Have we talked enough about that?
Does radians have a special symbol that you could use on the calculator, or?
No.
Yeah.
You just have to make sure you're in the right mode.
Okay.
Depending on how evil your teacher is. I had a teacher who constructed a quiz. So normally you could tell if you're in the wrong mode, because you'll get something like the guy had to be -7 foot tall, right? When you put the wrong units in. But you can construct it so that the answer comes out to make sense anyway. So be really careful. If you're putting radians into your trig, it's got to be in radian mode. If you're putting degrees, it's got to be in degree mode. Let me know if you're not sure how to change the mode on your calculator. Okay. All right. Anything else about radians and degrees and all that? Okay. So I think the next place I want to go is, let me try to balance this out a little bit. Any math related questions? Been on sort of a, well, this has been sort of math and science. No? Okay. All right. So let me erase this. Let me take us trip down vectors, and then I'm gonna kind of check in with people and see if they have any specific things they need. All right, let me know if you need anything. I'm gonna erase all this. Here it goes. All right. Yeah. Real quick, before I forget, one last thing about radians. If I have an expression like this, x cosine x, right? Let's say that I have a function that's like this, right? There is only one unit that makes sense to use here. So I really want this to make sense. Can somebody tell me real quick, what is cosine of 30 degrees? Let me do a little side note. Somebody remember how to think of that real quick? Now, let me give you the whole picture here. What is cosine like again? When is cosine biggest? Where does it like it? What is cosine like?
X.
X.
So the closer the angle is to the x-axis, the bigger the value of cosine will be. So this is either 1/2 or √3/2. And I know it's √3/2 because 30 is closer to the x-axis. With me? That's kind of like what I was doing earlier. Cosine likes x, so it gets bigger the closer to the x-axis you are. 30 is really close, so it's going to be its relatively bigger option. All right, got a chat there. Oh, somebody just tell me x. Okay. You guys got to let me know if something kind of doesn't make sense.
I have a quick question,
Yes.
but not really on the concept, I guess. Just more like something to simplify the process, I guess. But you know, when you did the pi r equals 180 degrees, and then you divided that by 6, and then you could tell that pi over 6 was 30 degrees, right?
Yes. Yes.
Is there an easier way to do that, to tell if cosine of this degree is this on the unit circle without actually looking at the circle?
Here's a beautiful. Are you talking about just how to like transform, how to convert from any degrees into? Okay.
But without like looking at the unit circle.
Yeah, of course. You just have to remember this. This is sort of the same thing as remembering that 1 foot is 12 inches. Let me show you why. We all know that 1 foot is 12 inches, yes?
Mm-hmm.
How do I convert 35 inches to feet? Has anyone ever seen this thing I'm drawing right now? Little grid? Very often.
12.
Yeah.
Yeah, so I would put inches here so it would cancel. I want to go to feet, and then I would put the numbers in, and then I just have to do what the math tells me. It tells me to divide here because 12 is on the bottom. Yes?
Mm-hmm. Okay,
now, what does that have to do with radians? So then the answer here would be whatever the hell 35 divided by 12 is, right? I think it's 2.83333333. Somebody can check me. You can never trust the math person to do math in there. Now,
2.91.
What is it?
2.916666.
Oh, that's what I did. I should have subtracted 833. Wait, okay. I was pretty close. I can use this the same way we used this. So if I have 30 degrees and I want to convert it to radians, don't I want to kill the degrees? I want the degrees to go away.
Yeah.
Yes. If I want to convert it to radians, I want the degrees out of there. Yes.
Mm-hmm.
Okay. So if I want degrees to die, I need to put them down here so that they'll cancel. So then I can put up here radians. And now what's the correct thing? How many what's in what here?
Pi over 180.
And 180. And of course, 30 into 180 goes how many times?
6. Okay.
So this is pi over 6 rads. Yeah.
Oh, okay.
Yeah. Now, with stuff like 30, you should kind of be able to think 180 divided by what is 30? That's 6. That's pi over 6. Do you see what I'm saying? But when you get some funkier degrees, if you ever do, like if they wanted you to convert 21.97 degrees into radians, you would do it the exact same way. You're just going to get something grosser, of course, right?
Mm-hmm.
Then you might even have to multiply pi in, depending on if the problem wants you to give an approximate answer. Okay, so that's kind of up to your teacher. But you can use that exact same process, doesn't care. That's what that process does. Takes it from degrees to radians.
Okay.
Is that okay with everybody?
Yeah. At least for me.
Okay with you, Eric.
Yeah.
Everybody else. You guys still with me out there? Man, this takes me back. I'm so happy to be back on campus. At least a lot of you guys have your picture, so you're not just a black box with the name on it. So that's kind of nice. Okay. Oh, I got a lot of chats. Yes, sir. Yes. Okay. And you don't have to turn your camera on, but if you can, that would be much appreciated. It helps maintain my mental health when I see humans, but you don't have to. I'm not putting a guilt trip on you. Okay. What was I about to do? Oh, yeah. So right here, what did we just figure out? 30 degrees is the same thing as pi over 6 radians, right? Now, in general, let me ask you something. Is this in, do you see this 11 up here? is that radians or degrees? If you saw like sine 11, what do you think? Is that radians or degrees?
Radians?
Yes, when it's not says degrees, you assume it's radians. If they meant degrees, they should have put a degree on it. So we normally don't write the little RAD. We don't have to, because if it doesn't have degrees on it, for right now, you assume it's radians. So what's cosine of pi over 6 then? This should take no work. What is pi? Yeah, go ahead, sorry.
Is it 60 degrees?
No. Stop. No. I'm not asking you to convert from radians to degrees. What is the cosine of pi over 6? Well, what is pi over 6? Isn't pi over 6 30 degrees?
Mm.
Okay, so what's the cosine of pi over 6?
Is it the same, the square root of 3 over 2?
Yeah, same. Okay. So my point here is, when I put something inside of a trig function, it doesn't care if it's degrees or if it's radians or if it's some other made up unit, as long as what I'm putting into it is an angle measure. That's all that cosine and sine and all the trig functions care about is, you feed me an angle and I'm going to tell you the ratios of the sides. That's what they do. So, but look at this function that I wrote up here. Is the x only inside the trig function? No, there's a part that's outside. And what's the only unit that is both an angle measure and a physical measurement? Which unit does that too?
Radian?
Radians. So whenever, that's why it's the preferred angle measurement system to use. It's because it could be put no matter where the variable is, in a trig function, outside of a trig function, because it's an actual physical measurement, not something we made up. Hopefully that makes some sense. Or if it didn't, oh well. This might come up at some point if in your class. We'll find out. Okay. So let me erase all that. I forgot what got me on that tangent. No pun intended. Okay, so let's talk about vectors for a little bit, unless anybody has anything specific that's come to mind related to this stuff. Okay, I don't hear anything. So how do I, first off, if I have a vector, let's kind of do this list backwards. If I have a vector, what do I need? Now some of my math people, depending on which math you're in, you could be working with vectors or not working with vectors at some point this semester. But if you've taken pre-calculus, you should have talked about vectors. So we'll see. So this is mostly geared towards my science people, but we'll see. What two things define a vector? Can somebody tell me? Any science people out there?
Is it distance and direction?
Yeah, what do you mean by distance? The direction I agree with.
Like,
What's the technical name for what you're getting at? So it's not really distance, because it could be the strength of a force, and it's actually not moving anywhere, so it's no distance. Go ahead.
Is it magnitude?
Magnitude. All right, now somebody else tell me, what the hell does magnitude mean?
I want to give it a shot in the dark, but I want to say like the domain, maybe.
That's interesting. No. You can talk about vector valued functions, but let's not go there. So direction makes sense. Direction is kind of like related to some given direction. I can tell you that this is like 40 degrees off from straight across, right? This would be like angle of ascension, right? So it's 40 degrees, angle of elevation. So it's 40 degrees up. You guys with me? So that's kind of like the direction. And that angle could be off of some other axis that's given in the problem. Yes, go ahead. I'm sorry, I cut somebody off.
Is it how fast?
It could be. So the magnitude, depending on what the vector represents. So the vector could represent speed, right? Velocity, let's say, let's be more precise. In which case the magnitude, so if it was a velocity vector, then the magnitude would represent the speed, and the direction, you know, the angular would represent exactly what we think of in terms of direction, the direction this thing is moving, right? Can we stop for a minute? It could be wind speed, though. It could be a force that's being applied, right? So the magnitude in the case of a force would just be what's another word instead of magnitude? How strong the force is, how much the force is, right? The magnitude. So in this case, has anyone ever seen like wind flow? Have you ever seen like a website that shows you the wind flowing and it's got longer arrows for stronger, for more forceful winds, for faster winds? Yes. So in this case, the length of the vector represents the relative strength of the thing I'm measuring. Okay, maybe. You guys okay out there? Anybody who's done vectors, you've definitely talked about these two things. Now, let's say that I'm given this, let's just say this is a 10 Newton force being applied at a 40-degree angle with respect to the horizon, right? So I could be applying this to a crate that I'm pulling or something. So let's not make it anything specific yet. Have you guys done any work with finding the components of the vector? Maybe?
Sounds familiar.
Sounds familiar? Okay. What do the components mean? I've kind of drawn them in already. How many components are there to this vector?
2.
2. What are they? I mean, can you kind of tell me where they are in this picture?
The 10 newtons and the 40 degrees.
Oh, I see. No. I appreciate that though. That's not a bad guess. So the components would be, you could call them, yeah, it would be the x direction. So let's call this the force. So this would be the force in the x direction. This would be the force in the y direction. And no, we're not talking about partial derivatives. I'm sorry. It's just the way I want to write it right now. So it's the x piece of the force and the y piece of the force. Now, so what's funny is when you start getting into these problems, there is one trig function that is used more often. Well, let's see. I'm getting ahead of myself. How do I break this up? So let's draw this triangle out. Let's look at it purely as a triangle. So I got an x piece and I got a y piece, and this is 40 degrees. Can somebody give me a way to figure out the x piece?
Cosine.
Yes, because cosine likes x. So what would the cosine of what?
Of 40.
Yes, good, because the only angle I've got is 40. I could figure that angle out, but it's not in the base, so I'm not going to use it. So cosine of 40, and what's by definition, what's cosine equal to?
X over 10.
X over 10. Kick ass. You guys good out there? I'm going to assume that's a yes. Okay. Can you use your, first off, do one algebraic step for me. How do I solve this for x?
Multiply by 10.
Multiply both sides by 10. I like it. So x is 10 cosine 40 degrees. Can somebody figure out what that is in their calculator? Where's my calculator? Oh, shoot. I left it at school. That's good.
7.66.
This one's almost dead. Let's see if I can do this. 7.66. Let's see if I agree. Yes. Okay. All right. Yes, Eric, go ahead.
Could we bring it back a little bit?
Yeah.
Why did you write f next to the components of the vector?
Oh, just because it was I was saying this is a force vector.
Okay.
This would be like the x piece of the force vector, the y piece of the force vector. To be honest, I can't remember exactly, and it kind of depends on your teacher how they reference these parts. To me as a math person, I kind of made a joke earlier. These look like something we call partial derivatives, but yeah, it's kind of like up to your teacher how they want to talk about the x and y components of a given vector.
Okay.
Okay.
So it is like F dependent on like whether we're talking about velocity or like something else, or
Yeah. I used F here because I'm calling this a force. This could have been a velocity vector. It could have been, anything else that can be represented with a vector. Yeah.
Okay, cool.
So anything that has some quality to it that could either be big or small, some strength to it, something like that, that could either be bigger or smaller, that would be a magnitude, and that can operate in a certain direction, they can be represented as vectors. And to be really honest, you don't even have to have physical meaning. I mean, so we're not going to go there, don't worry. But I could tell you all about linear algebra and, well, I'm not going to. It's not what this is. Real quick, can somebody else, no worries. I'll tell you everything I'm not going to tell you, and then you can tell me how much you appreciate it. Somebody else that hasn't spoken yet about this problem, how do you get the y piece? I see, that's Eric, I had to take a second to realize that's an emoji kind of thing you're doing. Okay, how do I get the y piece? So we got the x piece, right? This is the x component of the vector. Can somebody give me the y component? How do I get the y piece?
Sine?
Yes. So this will be, if I start off with sine of 40 degrees, what would the ratio be that I could create?
Would it be
Y over 10?
Y over 10, I love it. So then you would just multiply. Now I'm going to try to show you a shortcut here. So then you can throw that in the old calculator. Let's see if my calculator can stay alive long enough for a little thing. All right, you guys help me out. What do you guys get? Make sure you're in degrees, right? Okay, that's what I get. And again, it's really, now you gotta be careful. 6.43 watts. 6.43 cats, 6.43 atmospheres, 6.43
Newtons.
newtons. There you go. Okay. And it kind of makes sense. Does it make sense they're almost the same? Yes, because at 45 degrees, wouldn't they be the same? Is everybody cool with that? 45 degrees, they're the same? Yes. So we're really close to 45, so it makes sense they're almost the same. Okay, I like it. Let me ask you guys something. All right, this is going to take some participation. It's going to require some participation. Let me see if I can help myself out here. Okay, wait a minute. Let me get the chat up here. And the participants. There we go. Now I got it. All right. Oh, I'm sorry. Oh, Eric, is that a hand up now, or is that from earlier? Okay.
Yeah, it's always that. Sorry.
No worries. Can you guys see? You guys know how to say yes and no in the where'd it go here? Let me stop sharing for a second. Okay. Oh, I see. There's Eric saying with a check mark. All right, and there's the X. I love it. So Eric just demonstrated to everybody. So can everybody give me a check mark? Do you guys see where to get that? If you're not sure, let me know if you're not sure where to get that. Eric's gone for coffee. Eric wants me to go slower. All right, let's see who I have not heard. Abraham.
I don't know where to get that check mark.
Oh, okay. Do you see at the bottom of your screen, you see where it says reactions?
Yes.
If you click that, one of the options is a check mark. Let me do it. Yay, look at me. Gani, Zarifa, are you guys out there?
Yeah, thank you.
Do you see where to get that little check mark?
Yeah.
Can you make it happen? Okay. No, at least I know you're there. Okay. All right, so everybody tell me this. The class you're in, how much of what we just did, has anyone done anything related to what we just did in the class you're in? If you have, put a little check mark. If you haven't, put a little X mark. And some of you decided not to vote. Go ahead, sorry.
I'm not sure if like finding the limit of a cosine counts or something like that.
Not really. Thanks for playing. Eric, remind me, you're in which class?
Calculus 1.
Calculus 1. Okay. So some of you guys will. It's coming soon, right? So I think Amber, you were saying not yet with the question mark. Okay, so it's coming soon. My other reason for doing this, obviously, is just to make sure you're all actually there, which is kind of nice for me. Let me see. How do I clear all? There we go. Clear all. Bam! All right, sorry. I got power. Let's go back to this. Okay. I love how it's all still here. Scheisse. There we go. So let me erase some of this stuff. So let's talk about this. So this is very useful. Let me show you a quick demonstration of how breaking things into components is very useful, which will kind of lead into our next thing we got to worry about. All right, let me get out of here. Go away, everybody. Actually, let me do this first. Let me do something more basic first, I think. What if we are given, yeah, let's do something really basic and then I'll up the ante a little bit. All right, so what if we had to combine, let's say there's a crate and somebody's pulling it this way at 90 degrees, they're pulling it with a force of 9 newtons. Somebody else is pulling it this way with a force of 5 newtons. Everybody with me? What would the resultant force be and in which direction? Resultant magnitude and direction. So real quick, can you imagine in your mind, there's something here, somebody's pulling on it this way and somebody's pulling on it that way. Somebody's pulling north, somebody's pulling east. Which direction is this going to move? This could be a box in the ground and these are ropes tied to it. Are you with me? So somebody's pulling it north and somebody's pulling it east. Roughly what direction will it actually move? Is it going to move south? Is it going to go up? Is it going to tunnel into the earth? Do you guys not like this question? All right, let me ask you this. I don't know what just happened. Are you guys still with me? What if I had a person pulling a crate north with 9 newtons force? Which direction will it move?
North.
North. Now, if somebody came along and started pulling on it to the east with a strength of 5 newtons, will it suddenly just start going east now? Or which direction roughly will it go in?
Northeast. More north.
Northeast, roughly. More, say it again. I love what you just said.
Northeast, but more north.
Why more north, of course? Because
stronger pull.
The guy pulling it north is putting more force into it, right? Okay, so what we want to figure out then is exactly what angle, at what angle is this moving in? And what is the resultant magnitude of the force, the total force? So what I'm really trying to figure out is if I replaced these two guys with one guy pulling on a rope, how could I make this box move with the same vector movement, right? What would the angle here be? And what would the strength of this be? What would the magnitude of this be? So would you guys agree with me that it would be more than, well, let's find out. I don't want to put anything out there yet. Okay. So how do I do this mathematically? What am I going to do? So I want to figure out the result. Have you guys ever seen this idea? So let me do this in two different ways. This is the way that I like least. I can kind of create a little box here, and that would be my resultant. I should have drawn that in a different color. Let me see. You can still do it, Jeff. There you go, buddy. Nice and blood red. Bam. Isn't that the way? It's not really drawn to scale. Are you guys with me? Is anybody gonna hurt me for that? Hopefully not. Obviously 9 Newton should be a little bit taller, but we're gonna go with this. Didn't I just create a very useful shape, considering this is all about angles and side lengths? What shapes did I just create?
A rectangle.
Okay, I made a rectangle. Yes.
Triangles.
I made a triangle. I like it. So let's make a complete one of these triangles. So let's focus on this triangle here. Make him fully fleshed out here. There. So this side, of course, is 5. What's this side over here? What's it got to be?
9.
9, of course, because it was created parallel to this dude, right? Now, first easy question. Easy question. Well, let me make sure everybody's cool with this. This was north. This was east. So what angle is down here? What angle is this down here in the corner? Let me uncircle this. Oh, shoot. Oh, that sucks. Oh, well, that's a good job. What angle is down there? Yeah, it's got to be 90 degrees because it's north and east. So they're 90 degrees apart. So this has got to be 90. So can somebody please just tell me, how would you figure out the magnitude of this vector here, which is really just the length of it? The length of a vector represents the magnitude of the force, of the velocity, of the electric field strength, of whatever the heck you're talking about.
Pythagorean Theorem.
Pythagorean Theorem. I love it. So set it up for me. So let's just call this F, R, or F resultant. So what would that equal?
5 squared plus 9 squared.
And then the one little thing, since I didn't square this dude, well, we could just square him, or you could put a square root. Is that cool? You guys okay with that? If c squared is a
yeah.
squared plus b squared, then c is the square root of a squared plus b squared. I like it. All right. So the resultant force would be the square root of
106.
106. I like it. And does that simplify? I don't think so.
No, it's not pretty.
No. And of course, I don't just mean is it a perfect square? I mean, like, is it square root of 50 where I could take and break this up into 25 and 2, right? You guys remember that? You guys remember this kind of thing here?
Yeah.
Everybody else, you guys okay out there? Does that look familiar?
Yeah.
Although with my horrible handwriting and I wrote it really quickly, I wouldn't blame you for like, I have no idea what you just wrote. Okay. Does everybody understand what we really just did is kind of the reverse of the first thing I wrote down. The first thing I wrote down, I told you what the force was, and then we broke it into its parts, right? Well, here, I know the parts, and I'm trying to put them back together. So there's this. Now, can somebody tell me how to get this angle here? What is that angle? How do I get it? What trig function would relate two sides that I know are correct? Because to be honest, do we know if this is really correct? Could we have made a mistake? Isn't it possible we could have made a mistake on this? Yes. I want this to make sense. These were given to me, so I know they're right. I feel really good about this, but there's still a chance I could have made a mistake. So let's use the numbers I was given. What trig function relates these two sides in the angle?
Would it be arc?
Oh, I see. Yeah. Okay. Arctangent. Is that what you said?
Yeah.
So the tangent. Let's kind of get our way towards arctangent.
Okay.
The tangent would be what over what? What's tangent defined to be?
Opposite over adjacent.
I like it. Or sine over cosine, right? Which means y over x, because sine likes y, cosine likes x. So what's the y side?
9 newtons.
9, I like it. And what's the x side, of course, is 5. So now, like you just said, if I do arctangent, which you can either write as this or, Jeff, this means the same thing. It's just that this is really strange. So this is the attempt we made to make up for the weirdness of this. Yes. This makes people think about reciprocal. But I don't know. What do you guys get? Do you know how to put that in your calculator? You got to let me know if we're doing something that you don't know how to do. Do you know how to find that in your calculator?
Why did you use arctan?
Oh, are you cool with this statement? Where'd that statement come from? That's the whole thing that got me going. Isn't that true about the angle? The tangent would be the y side over the x side?
Yeah.
Okay, so tangent of that angle is y side over x side. And then, so what did I do? So I did kind of skip a step. What did I do to solve for theta? Well, to solve for theta, don't I want to kill tangent?
Yeah.
And what kills me is I actually had this happen once. Can I just do this? Oh, yay, there's theta. Theta's 9 over 5 tan. Does that make any sense? I'm sorry. I shouldn't be using that tone of voice because that's it's an honest mistake somebody made, but it drives me a little crazy. That's of course complete shit. It's sort of like saying, let me solve this and dividing by the square root symbol. It's the same problem. Yeah? So what do I do to kill a function? I have to apply the inverse function. Yes? That is how I kill a function. I apply the inverse function. How do I kill a cube? I cube root it because they're inverses of each other. Yes?
Or both sides, right?
Say again? Yes. Whatever you do on one side, you got to do the other
both
side.
sides.
That's the whole.
Yeah.
That's the thing that's just everywhere. So if I do the however you like it, I kind of like this. I'm fine with this. I don't know if most sine teachers like arctan. That could be true. I don't know. Maybe I'll have to ask one someday. So I'm going to do it. Inverse tangent to both sides. So these kill each other. Die. They're like antimatter. Right? That's not good. And then I end up with this, and I just have to know how to plug this in my calculator. Right above the tangent button in the graphing calculator, there's an arctangent, like an inverse tangent. You guys with me? I don't know. How many of you guys use graphing calculators? Anybody? Or do you guys use, anybody use scientific calculator? So Mary Elena, Amber, Eric, and the rest of you use, does anyone use an abacus? An abacus? Anybody use your fingers and toes? What's happening? What about the rest of you guys? What do you do? We take a wild guess and we hope. Marbles, I like it. Tea leaves, graphing, you just graph everything on a sheet of paper. Yeah, man, that's rough. All right, does somebody know the answer to this? Have you figured it out yet?
I got 60.94.
And there is two things to be careful about, right? And again, it really depends on your teacher, how much to round. Is this a significant figures problem? So we'll just round to 2 places. If you round to 2 places, it's got to be a 5 there, right? Is that cool? If I can see my own thing, right? Yes. Now, what's wrong with what I've written so far? What's wrong with that? Anybody know?
No degrees.
Yeah, I've got to put degrees there because that's what that is. Did anyone get radians? Did anyone else try to do this? Can somebody get radians? Are you guys with me? Am I alone?
Yeah, it'll be a 1.06.
Yeah, if we round to the same places, yes, okay. And again, it's just, you could either convert this, but it's better just to put your calculator in the other mode. So you have to be really careful if there is a preference for one or the other. So you either have to know your teacher, or your teacher is going to put it down on each problem. It really depends on the teacher, how they want it. All right, now, let me make sure I'm remembering what I want to do. So what if we do a more complicated? Why was this relatively easy? Can you imagine something I could have done? One little thing I could have done that made this much harder? Anybody? Anybody? Can you guys imagine something I could have done to make this much more difficult? Why was this so easy? This was really easy, yes? Why were we able to do this? Why were we able to use trig functions? Because we made what in here? What showed up?
A right angle.
A right angle showed up. A right triangle showed up. Right? You guys with me? Now, I don't know if somebody out there saying this was not easy, but hopefully you guys agree this was relatively simple. It was Pythagorean Theorem and it was trig. When does Pythagorean Theorem and trig, what's the only kind of triangles they work on? Right triangles. Unless you use law sines, law cosines. I don't know if anybody out there knows about those. Okay. All right, so let me clear all this away. I'm going to do a more complicated vector one, and then I'm going to check in with my math people because I've kind of been focusing on science for a while. So let me clear all this away. Hopefully that was okay. So what if we had a more difficult problem? What if I had, let's see, a plane going at 45 degrees, and it's going at 500, well, it's going to say 500 miles an hour. Let's keep it with, let's keep it in, it doesn't matter. We'll just say kilometers an hour, right? We'll want to keep it in, good units. You with me? So a plane traveling northeast at 500 kilometers per hour. Okay. You guys with me? Let me erase those, what do you call them? Shoot. Little check marks. They're kind of like making me question myself. There we go. Okay. Everybody with me? Nothing's happened yet, right? This is nothing's happened. So plane is going northeast. That's why it's at a 45-degree angle between north and east. There's a wind blowing from the northwest. Well, let's make it, no, let's do more interesting. There's a wind blowing, how do I say this in a way that's not crazy? Let me just draw it. There's a wind blowing like this, coming in at
southeast
degrees. Yeah, so it's not exactly southeast. You with me?
Sort of, yeah.
So it's blowing from the northwest, sort of. You with me? It's not quite northwest because it's not at a 45-degree angle. Is everybody with me? So tell me this, if the plane is going this way and the wind is blowing from this way, what's that going to do to the plane's motion? It's going to be going
Slower.
How do you mean lower?
Slower.
Oh, slower. Yes, because part of this, now I'm going to give something away a little bit. This piece of the wind, isn't it working against this piece of the plane's motion? Let me see if you guys understand what I just said. This piece of the wind is working against this motion of the plane. You guys understand what I just said? If I have, I really want you guys to understand this. If I have wind blowing at an angle, that means it's got a component going this way and it's got a component going that way. Now, what's true about this component of the wind and this component of the plane's motion? Are they working against each other or are they working together?
Working together.
working together. So that's why I actually don't even know yet which one's going to win. So part of the wind is slowing it down, but part of the wind is speeding it up. But it totally is going to make the direction I'm moving in different. Yes? And this is why if you fly a plane, you've got to know what the speed and direction of the wind is, because otherwise you're completely off target. Yes? Okay, maybe. So this is going to be a little more difficult than the problem we just did. Does everyone agree with that? All right, so let me show you a couple things, and then I'll open it up to my math people real quick. So here's my plane, and now does anyone? I don't think you've done much with this yet, but normally when you're adding two vectors, what I'm trying to do is I'm trying to add these vectors because the wind is working with and against the plane. I want to add the vectors. So what I normally do when I'm adding vectors is I draw one of them tail to head like this. So I took this vector and I put it right there. And I took this vector and I put it right there. Now look at what this does. Where's the result going to be? The result is going to be there. I didn't say how strong the wind was, did I? I probably should say something about that. What makes sense? Let's say it's a pretty rough wind. Let's say it's 80 kilometers per hour. Yes. Okay, so we got 500 kilometers per hour here. We got 80 kilometers per hour here. So this red line should actually be maybe a little bit shorter. Are you guys understanding what's happening so far? Are you guys okay out there?
Yeah.
Where Elena's okay. Okay. Connie's okay. And everybody else is just there. Okay. So this does not answer the question specifically, but it does well enough for me to kind of get a feel for what's happening. So how the hell do I convert this picture into work to get the actual answer? Why was the, let me do this. And I'm really sorry, but I'm going to do a little side note. Why would this question be much easier? What if I had a plane going 10 kilometers per hour east and I had wind going 5 kilometers per hour east? What would the resultant speed be?
I want to say 15.
Yes, of course, right? Yes, right? If you're in a canoe, let's do it this way. If you're in a canoe going 10 kilometers an hour and you start, or not a canoe, let's say a boat, going 10 kilometers per hour that way, and you start running forward 5 kilometers an hour, how fast does it look like you're going to somebody that's on the shore? It looks like you're going 15 kilometers per hour. Does that make sense?
Yeah.
Because you're standing still, it looks like you're going 10, and then you start running 5, it looks like you're going 15. Okay. All right, I like it. So why was this so easy? Because they're both going the same freaking direction, right? So now watch this. I kind of gave this away a little bit. And trust me, I don't think you're quite there yet. But I don't know if you noticed your teacher was here earlier. I'm sure you guys noticed.
Yeah.
He was in there kind of messaging me there. You were about to get into this. This is such a beautiful idea. If I can take each vector and break it down to what I'm going to call a VE, let's call it VX and VY. E was for east, but I'm not going to worry about that at the moment. You'll see. If I break each one down, let me rewrite this one a little bit better. Let me do it here. So here's my 20. So I can get a V. Why did you do that like that, Jeff? Hold on. I can get a VX, Jeff, VY, and a VX for that. Why did I draw it so tiny? I'm really sorry. Let me try this again. Okay. So here's my wind. at 20 degrees. Still kind of tiny, but that's all right. We're going to make it. So this would be Vx, and this would be Vy. I really want this to make all the sense of the world. If I do that for both, couldn't I just add these two together? Because they're both in the same direction, yes? Maybe? No? And then I could do the same thing. Oh, you're the one. Okay, you're okay. Don't worry. No worries. All right, let's just try this out. Can somebody please, so let's focus on this. X direction. Wind, plane. What is the X direction piece for the plane? How do I get this? And this is the thing real quick, this is the thing I forgot to point out earlier. I really want this to make a lot of sense. Let's do this the long way, and then I'll show you the short way. Somebody was about to say something. I'm sorry. Did you have a way to do that?
Would it be cosine?
Cosine. Okay, so if I want to figure out for the plane, it would be cosine of 45 equals Vx over 500, yes? This happened exactly like this before. And then did we multiply the 500 up?
Right.
So the X piece is the whole thing times cosine of 45. So the cool thing is, if you know the hypotenuse, all right, now listen, this is not technically correct, but I personally think of cosine as the percentage of this that lies in the X direction. So look, if I take the whole thing times this percent, I get the amount that's in the X direction. Cosine is not really a percentage, so I'm sorry. This is not technical language. It's just what made sense to me to keep things straight. So somebody help me out. What is that? Scheiße. Oops, my calculator is about to die. Is somebody answering the question? No?
353.5.
I like it. 353 point. Looks like a couple places.
Sorry, could you tell me or tell us how to change our calculators from degrees to radian?
Oh yeah. Do you have a TI?
TI 84, yeah.
Okay. Do you see the mode button that's right next to second?
Gotcha, yeah.
Look at it should be the third or fourth thing down.
Okay,
Radian,
just radian and degree.
Yep. So
Okay.
you just put the thing over what you want and then hit enter so it highlights.
Okay, perfect.
No worries. All right, now what about, so how can I do the wind quicker? The wind's X piece, let me put this down here, 80 kilometers per hour. So it would be 80, Vx for the wind would be 80 times cosine of 20. Is that cool? I would take the total times the cosine to get the X piece. So if I took the hypotenuse times the sine, I would get the Y piece. I really want that. The more you understand that, the easier this is going to be when you hit this in your physics class or your math class. Right? We do this stuff in math too. So what is 80 cosine of 20? Crappity doodah. I have no idea how much I can get more out of this poor little thing.
75.17.
What did I do? Oh, I see. When I was telling you about how to change it, I changed mine to radians. I was about 75.18. Is that what you said?
Yeah.
Okay. Now I'm kind of all over the place, and that's my fault. I'm sorry, but this is what happens when I'm talking and writing. It kind of goes all over the place. What I just did is I just took this X piece and this X piece. Do you see how this is really nice? This is nicer. I can't even take credit for this. I'm just lucky. Do you see if I took this X piece plus this X piece, it would be the X piece of the green of the result. you see how it would be the total x piece of the result? And it should make sense. If I break every vector in my problem that I need to add into x pieces and y pieces, I add up all the x pieces, I add up all the y pieces, and then we'll see what to do when we get all that together. Okay. So what is my resultant x direction is going to be this plus this. So let's see, what is that? Plus 353.55. And again, little caveat, you got to be careful about rounding. It's up to your teacher what they tell you, right? So we're being a little bit loose here with the rounding, but that's fine. We're just focusing on the trig. So now I know this for my green. Wouldn't it be good to know what the shit that is, right? And then we can do just like we did the very first vector problem we did. So how do I figure that? Well, if I knew the y piece of this guy, and in this case, I'm going to subtract this one, correct? Eric, go ahead.
For adding the resultant together, what would be like the situation for subtracting it, or would we not?
Oh yeah, that's exactly what we're gonna have to do now, because this is acting in the opposite direction, right?
Okay, yeah.
So some teachers will tell you to change the angle. To me, if I just draw the situation, I can tell when they're acting with each other and when they're acting against each other. Now, obviously, what's true about this y piece? Isn't it negative because it's going down? Isn't this sort of like in the fourth quadrant? Are you guys with me at all?
Yeah, I get that.
Yeah.
So be down 20. So this is actually negative 20 degrees. So if you put that into your sign, it's going to come out negative. Or you can just say, oh, whatever I get, I got to subtract it because I can see it on my picture, right? Maybe?
Yeah.
So this is nice. It's just small, and I'm sorry it's so tiny, but this is kind of hopefully showing you this was from the plane, this was from the wind. So together they make the x piece of the answer. So if I could just get the y piece of the answer, okay, so that's the plane minus the wind. That would give me the y piece of the answer. Then I can put those together with good old Pythagorean and do an arctangent and get the angle. It just becomes a problem like that first problem we did. So let's look at the y direction. Okay. So what is the Vy? Oh shit. What's the V? Let me write my little wind and plane down. I got to keep an eye on the time too. It's probably overtime now, right? What time? Yeah, this is about when we were supposed to end. It's fine. I can go a little late. Wind, plane. So how do you get the y piece of the plane? So look at the plane right here. How do I get the y piece? Which trig function likes y?
Sine.
So I would take 500 times sine of the angle, and that's going to tell me how much of 500 is in the y direction. I really want this to make sense. When you multiply a hypotenuse by the sine of the base angle, it tells you the amount of the hypotenuse is in the y direction. It is not a percentage, but I just decide to think of it like sine is the percentage of the hypotenuse in the y direction. That's not really correct. You hear what I'm saying? It's not really a percentage, but it sort of acts like it. So why not remember it that way? And what the hell is that? Let's see. Oh yeah, we already know what that is. It's gonna be the same as this. You guys see that? Because sine of 45 and cosine of 45 are the same thing. Go ahead, Eric.
Shouldn't the wind on the x direction been subtracted because it's going against it, or is it because it's still going along the x?
The x direction was going with it, right?
Okay.
It's the y direction. It's the y direction that's going against. So this is what we're going to have to subtract, the y piece, because the plane wants to go this way for the y piece. The wind wants to go this way for the y piece. Is that all right?
Sort of. I just figured because the angle underneath where it says wind blowing, the 80 kpl with the 20 degrees, That's, you said that's going down, so I figured it would
It
be
totally
in
is going down.
contrast to,
Totally is going down, but this is the y piece that's negative. The x piece is positive.
okay, so it's still going right, so it's considered positive.
Yeah, so this
Okay.
wind is just like this current speed, right? If I'm going 10 kilometers an hour and the wind and the current's going with me, I'm going to add, right?
Okay. Yeah.
Yeah, so that's happening in the x direction. The wind is blowing this way in the x direction, and the plane is going this way.
So if the plane was
Yeah.
going the other way, it would be subtracted instead?
Yes,
Okay.
totally. So that's
perfect.
exactly what's happening with the plane. Wants to go north more than south, obviously, right? It wants to go north. It's got a north piece to it, doesn't it?
Mhm.
And the wind has a south piece to it, doesn't it?
Okay.
Okay. So what is the wind's y piece? How do I figure out this y piece? Well, it would be the hypotenuse times which trig function of 20?
Sine.
Sine, because I want the y piece now. All right. So what is 80 times sine of 20?
27.36.
I like it. 27.36. Now, what is the resultant? How did I write it over there? Let me do this. VRX. Oh boy. So what is the resultant in the y direction? It would be this plus this. Forgot my units. Okay. 380.91 is what I get. Now, if you will forgive me, I am going to have to destroy some of this so I have some room. There's so much up here. I'm going to take all this stuff here away. So what do I have now? I have figured out that my plane is going to be going, come on. All right, let me draw this. Scheiße. In the x direction, it's going this, 428.73. In the y direction, it's going 380.91. So what is the resultant? We just did this, didn't we? This was the first problem we did with the vectors, right? So let me write this. This is parallel, right? So I can put this over here. Don't I have a nice triangle to work with? How do I figure out how fast my plane is going? How do I figure out this piece? Magnitude.
The 428.73 squared.
Yes, so I have to do good old Jeff. I have to do good old Pythagorean Theorem. I really want this to make sense. I know this is a lot to throw at you, but I don't care how many vectors you have working with and against each other. Take all the x pieces and add and subtract them. Take all the y pieces, add and subtract them. You end up with this and this, or this, you know, and then you do exactly what we're doing. You do Pythagorean to figure out, put them all together into one hypotenuse, and you do inverse tangent to figure out the angle. It's so beautiful. I don't know if you guys agree with me. Are you guys cool with this? Has anybody ever seen this symbol? It means the magnitude of the velocity. It looks like absolute values because they're actually related. And this would be square root. All right, let me see. I just threw a lot at you. Okay, take care. Nasir. I'm desperately trying to get to a point where I can talk more math. Let's see. And whatever the hell that is, I almost don't care. Let's see. Just for completeness.
573.49.
I'll take your word. It sounds good. 573.49
Yes.
kilometers per hour. So we sped up a little bit. I don't know if you guys remember, but the plane was going 500. So with the wind, we actually sped up a little bit because the part that was working with me was more than the part that was working against me. Now, what angle are we going at? Who remembers how to do that?
89.90.
How'd you get that?
I did the arctangent of
Good.
573.49.
Arctangent. No, be careful. No, no, no. What's the tangent of this angle? Wouldn't it be this divided by this?
Yeah.
Yeah, so that's what you got to take the arctangent of, is this ratio. Right? Maybe that's what you did. I don't know. Oh shit. Whoa, I just did something really weird. All right. 380.91 divided by 428.73. I get an angle of 41.62 degrees. Okay. So it kind of makes sense. I was originally going at 45 degrees with the southwest wind or southeast wind like that. It pushed me down to 41 degrees, almost 41.62 degrees. So that kind of makes sense. I know this is a lot. And by the way, I am recording this. Did I remember to start the recording? I think I did. So I will email
You
out.
did.
I will email out the link. I'm going to put it up on YouTube, so then you can rewatch this if you want to. All right. So now I want to hit my math. Do I have any math people left over? I don't know if my math people all left.
Right here.
Who's this? Oh, Eric.
Yeah.
Was there something you needed more of? You probably didn't need as much vector talk, so I'm sorry, but this is still pretty good.
I think I do actually have a couple questions. One of them's about this, though. Your example.
Okay.
You said for the y direction, you said we're going to subtract there.
Yes.
It looks like we added it. You
Oh,
said
did we?
Aren't we supposed to take 27 from 353?
Thank you. Look at me. I was telling myself not to forget this. So yeah, you're supposed to subtract there. So everything here is a little bit off. So that's my fault. Thanks, man.
I should have told you earlier.
I see. No, you're fine. You're fine. So that's my mistake. I kept saying it, and then of course I forgot. Good job, Jeff. I should have put this here immediately, which is what I normally would do, just to remind myself that that's negative, that that's going down, right? So we could redo it all. It's basically the same work. It just, the numbers change a little bit. Okay. So it's not on you to get that right, but I appreciate you pointing that out. Anything else, guys? Oh, go ahead.
What's the point of the absolute value?
Oh, that is the official symbol for, so if I have a vector, vectors of course look like this. I don't know if you've seen this symbol before for vectors. To be really honest, this just means the length of a vector. Now tell me real quick, what's the absolute value of negative 4?
4.
Because the length of the vector pointing to negative 4 is 4 long. We don't say the word vector when we first teach absolute value because we haven't talked about vectors yet. But that's why the absolute value symbols actually mean magnitude. They mean length because it lines right up with what we understand about absolute value.
Okay.
You're welcome, Amber. Okay, what's your other thing? I'm going to clear all this. Are you guys ready? All of this is going to go away.
I got everything I need for that.
So if you're watching this in the future, I should have subtracted here, which would make this number different, which would make this angle a little different, which would make this magnitude a little different. And I always love when I do that, especially when I'm supposed to be instructing. I love making a mistake then, but I'm human. So I'm going to clear all this away. And then what's your other question about?
It's I'm kind of bringing it back quite a bit to the beginning. You said earlier.
Take care, Marilena.
I think earlier you said tangent was sine over cosine.
Yes.
Right. So, first off, what would be like sine and cosine? Would that just be like, cosine would be like tangent over sine or something, or?
Here's their basic definitions, right? So to be really honest, what we did is all trig functions are various ratios of sides of a right triangle. You with me?
Yeah.
That's all they are. So I could put y over the radius, I could put x over the radius, or hypotenuse, whatever you feel, or I could put y over x. But isn't y over x, isn't that equal to y over r, x over r? Like the r's would cancel, right? Do you see how the r's would cancel?
Mm-hmm.
So, and isn't y over r sine? And isn't x over r cosine?
Okay.
So we just realized that if we do this work to get tangent, I could just divide the two numbers I got. I don't have to look back at my triangle. Or of course, if I don't have a triangle and I just know sine and cosine, well, thank God I know tangent sine divided by cosine. Does that make sense?
Yeah, no, it does, yeah.
So it's not really because it's defined this way. It's really is defined to be ratios of sides of the triangle. We just noticed that y to x is the ratio of sine to cosine. So that's another definition of tangent. Okay. And of course, I didn't even bring up cosecant, secant, and cotangent, but you're cool with those, are you?
Not really, to be honest.
So sine, so let me write this. Cosecant theta is 1 over sine theta. So it's really just r to y. Okay. Right? It's just the reverse of sine. Secant theta is 1 over cosine theta. So it's really just r to x. And cotangent theta is the easiest one to remember because it's got tangent in the name. Cotangent theta is 1 over tangent. So it's x to r. I'm not r, x to y. And how tired am I? Get out of here. X to y. Just the reciprocal of tangent, right? So these are not surprisingly called the reciprocal identities, reciprocal trig functions. Because they are just the three main trig functions reciprocated.
Okay. Why is it, that's probably a big question, but like, why is it 1 over sine for cosecant or for even for secant, all of this?
Sort of. All right. So there's a lot to the story, but based on what I've got up here, it was just an understanding. Like if I just said, how many ratios can I make from 3 sides? Y over r, y over x, x over r, x over y, y over x, x over r, y over r. Are you with me? Mm-hmm. Did I write 2 things twice? I did. The x over r. So 1, 2, 3, 4, 5, 6 things. So we've got sine, cosine, tangent, and then we got cosecant, secant, cotangent. They cover all the different ways to write ratios. These 3 just happen to be the reciprocals of the base 3. The base 3 are sine, cosine, and tangent. These are the ones that we just sort of automatically think of. They relate to these ratios. But of course, I couldn't have written the ratio the other way around, so we just decided to give those their own trig names. So is cotangent like the exact same thing as arctan, or? No, definitely not. The reason, in fact, did you say, sorry, multiply by like the reciprocal to get rid of it? Or? No, definitely never said that. Oh. You apply the inverse function to kill a function, yes. Okay. Because if I had this, how would I solve this equation? Would you divide by the cube root? I would cube both sides, right? Because cube is the opposite of cube root. Yeah. So they kill each other. Okay. So if I had this, I have to apply the, what am I trying to write here? It doesn't matter, Jeff. I have to apply the inverse trig function. This is a bad symbol to use because that does mean like 7 to the negative 1 is 1/7, correct? Yeah, that's what I was thinking. All right, so this is a bad symbol, but do you remember the inverse of a function? We use this symbol to represent the inverse. Does that sound familiar? Yeah. And that does not equal 1 over f, right? It's the inverse.
Oh,
So that's where this came from. We're like, here's the function. So we're going to use the same thing we did here. We're just going to put a -1 there. But then students think it's 1 over.
okay.
That's not what it is. It means the opposite of cosine.
Okay.
Which means, real quick, are you copying anything down? Can I erase all this?
No, not here, no.
All right, I'm going to clear all this.
Okay.
Bam. So what is, not to put you on the spot, well, what's cosine of 30 degrees? Do you remember?
I want to say, if you give me a second.
Sure.
Cosine, that would be...
Is it closer to the x or the y?
It's closer to the x.
X.
So
Is cosine like x?
I want to say pi over 2.
No. Okay.
Huh.
Pi over 2 would be a degree measure. Would be
Okay.
like an angle measurement.
Mm-hmm.
So this would be pi over 6. That's what 30 degrees is.
Oh, yeah,
Cosine-
yeah.
Yeah, so these are like the big outputs could be 1/2, rad 2 over 2, rad 3 over 2, 1, 0, right? Those are the common outputs for the angles we memorize.
Okay.
Okay. Cosine likes x. So the closer I am to x, the bigger the output is. I'm really close, so it's this one. If I was at 45, it would be this one. If I was at 60, it's getting smaller now. If I'm at 90, cosine hates it there because there is no x piece if I'm at 90 degrees.
Mm-hmm.
Does that make sense?
Yeah.
So that's what I'm thinking. If I'm like, to be honest, I don't have these memorized. If somebody says what's sine of 60, I go, all right, that's closer to y, so it's root 3 over 2. I don't have them memorized because I don't want to take up space in my brain. Okay, now, what was my point with this? I had a point. Shit. Oh, okay, here it is. So what's the input to a trig function? What physically is this? What is this a measurement of?
Of the circumference?
No.
Or the radian. My bad.
What is this? What have I drawn here? This is a what? What kind of geometric figure?
Oh, an angle.
Angle. Okay, so
Yeah,
the input for a trig is an angle, and the output is a number. Inverse cosine, the input is a number, and the output is the angle. That's what inverse functions do.
Okay.
So if I put rad 3 over 2 here, the output would be 30 degrees. Because you're saying to yourself, what angle does cosine need to make this? Because the answer is the angle that makes cosine give me this answer. It's the opposite of what I'm taking here.
That's why it's the reciprocal instead of the inverse.
No, this is the inverse.
Oh, that is the inverse.
Yes, it is the inverse. And it's an inverse because it didn't just flip things over, it changed the output input.
Okay.
That's what inverse functions do. Like, what's the inverse of adding?
Subtracting.
Crazy. Why? Because if I add 2 to 5, I get 7. And if I take that and subtract 2, I get 5. So see, this was the input, the output. If I put the output here now in the inverse, I get the input back. They undo each other.
Okay.
One guy's output is the other guy's input and vice versa. That's how inverse functions relate to each other.
So inverse is just the
function that does the opposite. Yes.
Yeah.
So what does a trig function do to an angle? It turns it into a number, correct?
Mm-hmm.
So sine of 45 degrees becomes the number rad 2 over 2. So what does inverse sine do to a number? It turns it back into the angle that would give me this. It undoes. So what did sine do to 45? Made it this. So what does sine inverse do to this? Brings it back to 45, but undoes what sine did.
Okay. Is there a reciprocal to sine?
Of course. And you know what it is. So we got sine theta, cosine theta, tangent theta. So the reciprocal of sine is what we call cosecant.
Okay.
The reciprocal of cosine is what we call secant. The reciprocal of tangent is the easy one.
Okay.
It's just cotangent. So the way I remember these is S goes to C, C goes to S. I don't know if that's going to help you. But
Okay. So if something like a question in my class asks me like what is the reciprocal of sine 45 that doesn't exist, or
no, so the reciprocal of sine 45 would be cosecant of 45.
oh, okay.
Yeah.
And so the inverse of sine 45 would be square
Well,
2
I want
over
you to
2.
understand. No, not the inverse, right? The inverse sine of rad 2 over 2 would be 45 degrees.
Oh, you can't have an inverse of a degree?
No,
No.
definitely
Okay.
not. What must the input to a trig function be? An angle, right?
Okay, I didn't know that. Okay. That it had to be an angle.
Has to be. That's what trig
Okay.
functions are built on, right? They're built on angles in triangles. So the input always has to be some angle measurement. So we talked about degrees, we talked about radians. Those are two things that could be inside of a sine or any trig function.
Okay.
The output is a number.
Okay.
Yeah. So for an inverse sine, that's backwards because that's what inverse functions do. They flip the input and output.
Mhm.
So for an inverse trig function, the input's a number, and it gives you the angle that would give me this number. It undoes. Yeah.
Okay. Yeah, that makes a lot of sense now.
Sort of like, what's the square root of 16?
4.
Because 4 is the number squared gives me 16.
Mhm.
Right? Isn't
So
that
it's
sort of
like the inverse of it.
so it's the inverse of squaring something.
Okay.
So the output becomes the input, and the input becomes the output.
Gotcha. Okay.
All right. I got to run.
Of course. I'll let you go.
All right. Thanks for coming out, man.
Thank you.
Take care.
Thank you very much.
Sure.
Have a good one.